tell us something about Everspin?
Okay. So, Everspin Technologies is a specialty memory technology. We manufacture a memory type called magnetic random access memory, or MRAM, and it's non-volatile. So if you turn off the power, it retains all its information. And we have commercialized, we're the only ones in the world that has actually commercialized two different types of MRAM. One is what we call the field switched MRAM, or toggle MRAM, and the other one is spin transfer torque, or STT MRAM. And we've been in production with toggle MRAM since 2006 and with STT MRAM since 2017 timeframe. We've shipped about 150 million plus units since our inception, and we are very quality conscious. So we really have single digit returns to talk about. So very quality conscious and good quality material.
Can you tell us a bit about MRAM and how is it different from other non-volatile memory storage?
So the way MRAM works is you basically have two magnetic layers that are separated by an insulating layer. And these two magnetic layers, they can either be oriented in the same direction or they can be oriented in opposite directions. So when they're oriented in the same direction, the resistance is pretty low. So that you have a zero state. And when they're in opposite directions, the resistance is high. So you have a high state. So binary, 0 and 1, and that's how you make a memory. What are the advantages of MRAM? Basically, fast read writes. So we can actually write and read on the order of 35 nanoseconds. We can write unlimited times, so unlimited read write cycles. And like I said, it's non-volatile, so you can turn off the power. And we can operate in temperatures from automotive to industrial to commercial. So now let's compare that to standard memories like battery-backed SRAM. So the first thing is if you turn off the battery on a battery-backed SRAM, you lose the information. And then you have pretty poor read and write cycles. So a million best case. Then you have non-volatile SRAM. There actually you have much more read and write cycles, but then it doesn't scale. It doesn't go to higher densities. For example, MRAM can go all the way from 128 kilobit to 1 gigabit. That's what we've been shipping for the last few years. Another type of memory is ferroelectric memories. Now, ferroelectric memories are basically charge-based memories. And actually, I happened to commercialize it. I was part of the team that commercialized it at Texas Instruments in 2005, 2006 timeframe. So I know that memory pretty well. I think it's very well suited for low voltage applications, for commercial applications. When you go to higher temperatures like industrial or automotive, it faces some challenges. So I think that's where MRAM wins out over all other technologies. If you're looking for something that is completely robust, minus 40 to 125 degrees C, automotive temperatures, unlimited read-write cycles, and trying to secure data in flight. So if you lose power, which memory would you use to quickly write the data on what the memory was doing? That would be MRAM.
Can you tell us about field switch MRAM and STTM MRAM and how are they different from each other?
So the first one that I said was toggle MRAM or field switched MRAM. And basically you can switch the free layer. So you have, like I said, two magnetic layers separated by an insulating layer. The top layer is what we call the free layer and the bottom layer is fixed. So you can switch the free layer by either applying a field or by passing a current through the insulating layer between the two magnetic layers. So when you switch it to a field, it's toggle MRAM, it's field switched. And when you switch it by passing a current through the tunnel barrier, then you have spin transfer torque MRAM. So what are the advantages? So with the field switched MRAM, basically you need a certain dimension to generate the field to be able to switch it. And that's the reason why it doesn't scale. So we offer that between 128 kilobits to 16 megabits. But if you wanted to scale, then you got to go to the spin transfer torque approach where you're actually passing current through the tunnel barrier to switch it. And there it scales with the CMOS node. So as the CMOS node gets smaller and smaller, the MRAM die size can get smaller and smaller. So from 16 megabit to 128 megabit, you can actually buy STT MRAM. And then also we have commercialized STT MRAM for DRAM replacement. There we go up to 1 gigabit. So that's the advantages.
Do you think that this technology can replace the existing non-volatile storage technology market?
So if you're looking at the different types of memories, if I'm plotting read-write cycles on the y-axis, and I'm plotting latency or access speeds on the x-axis. Storage is to the far right and in the bottom, right? It takes forever. Like think of your computers, right? The disks and the SSDs, they take forever to write, or the NOR flash, right? And they're very low in read-write cycles, maybe a million cycles. Okay, there we are not targeting those memories. On the left hand over here, with the large number of read-write cycles and very low access speeds in the nanoseconds, that's where you have DRAM and that's where you have SRAM. So those are the technologies that MRAM is replacing or can compete with. For example, like I said, our read-write cycles are 35 nanoseconds. That's as fast as DRAM, almost as fast as DRAM and SRAM. The other thing is, in between, you have this NOR flash memory, which is basically a microsecond or hundreds of microseconds of write time in very fast reads. We can do 35 nanosecond writes compared to the 100 microsecond reads. And that's where people are looking at replacing NOR flash with our technology. Also, NOR flash stopped scaling at about 40 nanometer CMOS. That's the reason why all these foundries like TSMC, Global Foundries, Samsung are now offering embedded MRAM as a replacement for embedded NOR flash or embedded flash. Where we come in is we offer standalone flash. So we don't compete with Samsung or TSMC or Global Foundries because we offer discrete or standalone parts, and they have the same problem. It doesn't scale for high densities, and it stopped scaling at 40 nanometer CMOS. So that's where Everspin and our MRAM is playing a role.
What is this standalone flash?
So standalone is basically you can buy a chip and put it on a PCB board. Okay, you can remove the chip, and replace it with another one, right? So it's standalone. Okay, and embedded is basically built into the CMOS, and you cannot actually replace it. Yeah.
What are the potential applications of this technology?
So if you look at our primary markets that we're targeting today, we call it the PERSYST brand. PERSYST is basically performance in systems. So PER SYST, performance in systems. And there we are basically going after the industrial automation market. So think about companies like Siemens and Schneider, which are our primary customers over there. So they use these programmable logic controllers to control the robots on the manufacturing floor. So if they were using regular memory when there was a power loss, the robots cannot tell the PLC what they were doing. So upon power loss, anything that is being manufactured on the floor is scrapped. With our memory, you can write back to the PLC in 20 nanoseconds, 35 nanoseconds. So everything on the floor is saved. So you lose power, all the information is in the PLC, turn it on, and the PLC picks up exactly where it was. Okay. The other example is in casino gaming. Every slot machine on the casino floor, every action has to be recorded 3 times in 3 different locations. And it has to be recorded as fast as possible. And that's where MRAM again comes in. If you're using NOR flash, it's going to take hundreds of microseconds. If you're using MRAM, you can do it in nanoseconds. So all the casino gaming industry, the industrial automation industry. The other one is storage industry. So wherever you use RAID memory, so RAID is basically, it's like metadata that is stored on the servers from whatever you're actually using. There we have captured a large portion of the market where most of the RAID memory is actually stored using toggle MRAM or STT-MRAM. Another example of the PERSYST is in battery management systems for EVs or engine control units in EVs, right? That's where, again, you need fast logging of the data. How is the battery doing, right? The manufacturers want to know how the battery degrades or how the engine responds when the driver actually steps on the gas, right? So those are the things that need to be recorded very fast. That's where we're getting design wins. Another major design win that we have is we're actually designed or manufactured STT-MRAM to replace the DRAM market. And that we have a significant win with IBM, where we're actually designed into their flash core modules. And the idea over there is they use NAND flash, which is really cheap, right, for storing most of their data that they have. But any data in flight, they actually store it on our STT-MRAM. And when they power down the system, when nobody cares about what's going on, they download all of that data into the NAND flash offline. So they don't impact the latency for the customer. So we've been shipping to IBM since 2017. We are designed into the flash core module. We've gone from FCM 1, 2, 3, and 4. and there is a high probability that we'll get designed in for the next generation as well. So pretty good success with STT-MRAM and toggle MRAM.
In terms of cost, how is it comparable with the existing non-volatile storage?
So Everspin does not compete on cost with existing memories. We are a value proposition. And again, the example is you want to lose all the work in progress on the manufacturing floor by using a cheap memory, or you make an investment one time and instead of using a $10 memory, you use a $15 memory, and then you never have any manufacturing scrap on the floor due to power loss. So we compete on value, not on cost. So on cost per bit, you will always find that our parts are more expensive than an all flash or an NVS RAM or a DRAM. But whenever you want value and performance, that's where people will design in MRAM.
What are the challenges you faced in designing an MRAM and how did you overcome those challenges?
So first of all, we are a public company since 2016, but we are still a pretty small company. Our revenue in 2023 was on the order of $60 million. Okay, so for a large company like Siemens or Schneider to design us in can be viewed as a risk, right? So the way we went in about getting our design wins was our parts are pin compatible with our competition and fully socket compatible and software compatible with our competition. So our sales pitch from the very beginning has been, you can design us in for performance, and if you're concerned about Everspin, you can always remove that part and put in another part, and your operations are not interrupted. So that's how we've gone about making our sales, that we are wholly compatible with our competition, but we bring value compared to our competition. That's how we have grown our design wins in the industry.
What is XSPI and how is it significant to MRAM?
So XSPI is basically our way of saying that X can be quad, it can be single, or it can be octal SPI. So it's a variable X, right? Most industries, most of our competition will talk about quad SPI or single SPI. We are the only ones that actually have an octal SPI with MRAM. Nobody else does, with speeds of almost 400 megabytes per second. So pretty unique from that point of view. So now, why would people use XSPI or a SPI interface compared to the random access interface? So our earlier parts were with a parallel interface, which is random access memory. But the idea is you need a lot more input-output terminals, right? So it becomes very large. So to get over that, people have gone to XSPI or a SPI interface, which is basically by 8 or by 16. And that way you can actually minimize the number of input outputs. An extreme example of that is DDR, right? There is another way of reducing the number of terminals you need and getting a lot of data in and out of a processing unit. So that's the reason why we've gone from parallel interface to a serial interface with our newer parts.
What are the key considerations while designing the MRAM?
So like I was talking about earlier, we have made sure that our memories are compatible with existing solutions. So for example, when we brought out this 64 megabit STT-MRAM part last year, we actually made sure that the controllers were also available with that MRAM part. So we built the controller for the octal SPI because we knew that nobody else had it. And then we made sure that the controllers that are out there are compatible with our technology for quad SPI and single SPI. So you have to think about the ecosystem and build the ecosystem along with the memory. And that's what we have done. So we build the ecosystem along with the memory, with the component memory at the same time.
What is the significance of radiation hardening in aerospace applications and how does MRAM help there?
So when you send all these memories on spaceships into deep space, they're exposed to alpha radiation. And if you have a memory that's based on electric charge, those alpha radiations can change the electronic states of these charged states. And that actually causes a disturb. And like we were talking about earlier, magnetic memories are not electronic charge based. They're actually the spins of the electrons that determines the state of the memory. Okay? And they are not impacted by radiation. And that's the reason why it's radiation immune. In fact, we are strategically radiation hardened, which means that our memories are not disturbed up to 1 million rad silicon. So it's pretty robust from that point of view. And that's the reason why we are designed in, for example, Today, we are actively collecting data from Mars on the Perseverance, and then also we are designed into the Lucy mission going to Jupiter. I just want to clarify one thing: we don't make radiation-hardened product, right? Our memory, our MRAM, is naturally radiation immune, but somebody has to go and radiation harden the silicon around the periphery of the MRAM array, and that's done by our defense industrial based customers like Honeywell or Cobham or Case or Frontgrade. Those are guys that actually go and make radiation hardened periphery, and we build the MRAM for them, and then that composite device is then radiation hardened.
What technology do you use for troubleshooting and optimization of the product?
So we have basically spent a lot of years trying to develop the technology and the expertise to understand the failure mechanisms in MRAM. Okay, and that's the reason why we can claim that we have shipped about 150 million plus units with single-digit returns for any field failures. So pretty high quality. And the reason is we actually understand our technology very well. We have developed very robust models, and because of that, we don't have any failures in the field. In addition, we actually have lead customers that we work with. They actually test out our part in the field, and they give us feedback. So every part that we bring out has a lead customer that works with us to work out the watts.
What future development do you foresee for this technology?
So there are two areas that we are focused on. One is what we just talked about. NOR flash stopped scaling at 40 nanometer CMOS. And for high density NOR flash, there is no alternative. And that's the reason why STT-MRAM plays a role over there. And that's actually for high densities above 256 megabit, actually above 128 megabit. That's a $2.5 billion market today. That's $2.5 billion. That's a huge market. And that's what we are focused on. We have one part that is in design today that should go into sampling next year or the year after. And then we'll be able to target that market in 2026, 2027 timeframe. The other thing is, there's all this discussion on AI inference, right? Think about it. Most of the power loss of the AI inference is because you're constantly refreshing your memory on the edge. And you're sending the data from the edge to the cloud and back from the cloud to the edge. If you can put a brain center on the edge, you don't need to do all of that. And if it's non-volatile, you can get out of the refreshing power as well. So that's what Everspin's MRAM brings to the table. So what we are targeting is a demonstration with our customers or with our partners that shows that you can actually use MRAM for AI inference on the edge. So that is something they're doing. And then the last thing is to address the data center market. With this AI, there's a large demand for compute memory, right? So the idea is, can MRAM be compatible with the new interfaces that are coming about, the UCIe interface, the physical interface, with the CXL protocol that runs over it? And we believe that MRAM is compatible, and that is another demonstration that we're working on. So hopefully that will be our next trajectory after the NOR flash replacement. It'd be AI inference on the edge and the storage industry that we're targeting.
What role do you see of MRAM in the future of aerospace development?
So aerospace is basically radiation hardened devices. So we have a huge role to play. In fact, most of the defense industrial based customers in the US and now also up to some extent in India as well as Europe, I understand, use our parts through our partners. For example, Honeywell or Frontgrade, which used to be Cobham or Case, right? So our parts are all over the place. They're being used in ISRO, they're being used in the US, in NASA, they're being used in Europe under the European Space Agency. So I believe with this natural immunity that MRAM has to radiation exposure and the robust technology that we have developed that actually works between minus 40 and 125 degrees C, I think we have a bright future. Given this explosion that you're seeing in low Earth orbital industry over the next few years, I think there's a large market, and it's a great opportunity for Everspin.
What are your future marketing strategies for further growth?
So we talked about that a little bit. So I think if you look at our current business, we talk about our persist memory, which is entirely in production today. That's on the order of $60 million as the end of 2023, right? And we plan to grow it to $100 million over the next 2 or 3 years based on the new products that we brought out over the last 2 years, the 64 megabit XPI and the 16 megabit XPI. Beyond that, we see this NOR flash market as prime from where we can actually grow our revenue significantly. So that's where we're marketing. We're talking to our customers, and the automotive customers particularly are very interested in the XPI interface and for all the electrification that's happening in the vehicles. They really need fast memory and they really need reliable memory. So today, as I understand it, most of the customers actually have redundancy. So if they need 128 megabit there of NOR, they're actually using 256 megabit of NOR. So they can actually replace the 256 megabit NOR with 128 megabit STT-MRAM and get the superior performance at the same time. So I think that's where our growth will come over the next 3 to 5 years. And then, like we talked about, AI inference on the edge and the storage market would be icing on the cake.
What would you like to say about the competition in this technology?
So today, we don't have much competition in standalone MRAM. Avalanche did bring a product to the market a couple of years ago, but we don't see them in the market anymore. And in any case, they only had a 16 megabit part. And like I said, we go all the way from 128 kilobit to 256 megabit. So a pretty wide range of densities. Similarly, there's a company called Netsol, based out of Korea. But again, they also have only a 16 megabit part. They don't have a wide range of products. So we don't see them very significantly in the market. So as far as standalone is concerned, we believe that right now we are the only game in town. And as far as embedded is concerned, we have licensed global foundries with our technology to provide the embedded solution to their customers. So every time they sell a wafer, we make royalty on every wafer that they sell. So it's a steady revenue stream from a royalty perspective as well.
What role does media play in telling people about the technology?
Media plays a critical role. And the idea is, I mean, you have to get the word out, right? So this is the best way to get the word out. Gives me a platform to talk about my technology, gives me a platform to talk about what I'm passionate about, and gives me a platform to talk about how we bring a new solution to the market. I mean, we can talk about the pros and the cons. We can talk about what's coming in the future. It's a great platform. Yes, marketing plays a huge role and media plays a huge role in any company, especially Everspin.
Can you tell us about any product of your company which might be a game changer?
Yeah, so the 64 megabit XPI and the 16 megabit XPI that we brought to the market, that is a game changer. If anybody in the PLC market, in the automation market, is looking for a high density part with MRAM characteristics, that's the only one that's available. We are the only ones that actually have an octal SPI 60. But yeah, I mean, we do have that. And then next year, like I was talking about, we'll have this 1 gigabit part that we call it enhanced NOR replacement. I think that'll be another opportunity to highlight the capabilities of that. Yeah, that's about it.